Now, despite the fire and the ash, which is technically called, and here's a new word for you, a pyroclastic flow, this is not a volcanic eruption. Officials say people were never in danger. The lava was just too far away, although it was an issue briefly for some of the aircraft in the area.
The alert arrived without drama, a quiet shift in data that only machines were trained to notice. At Mount Etna's monitoring center, a thin line on a seismic graph bent slightly out of pattern, then held there, stubborn and wrong. No alarms sounded yet, but several scientists straightened in their chairs at the same time, their instincts sharper than any software. The signal did not resemble the familiar prelude to an eruption. It lacked the vertical punch of rising magma and instead spread laterally, a sideways whisper moving through ancient rock. Etna was not pushing upward. It was pulling itself apart. Within minutes, additional stations began reporting similar distortions. The changes were subtle, measured in millimeters and microseconds, but their alignment was unmistakable. Something deep within the volcano was migrating along a plane that had not been active in recorded history. One volcanologist pulled up historical maps, overlaying modern data onto centuries-old fracture patterns. The overlap was chilling. The mountain was awakening an old weakness, a scar from a collapse long before satellites and sensors existed to watch it happen. Outside the observatory, the mountain looked serene. Snow clung to its upper slopes, and the sky above Sicily was clear and pale. Nothing about Etna's appearance suggested urgency, which made the numbers on the screens feel surreal, like they belonged to another place entirely. Gas sensors chimed softly as concentrations rose in areas that should have been stable. The gases were not eruptive plumes, but seepage, bleeding through microscopic cracks that were widening under immense pressure. The mountain was exhaling through pores that had been sealed for ages. A low-frequency tremor followed, too gentle to rattle windows but strong enough to vibrate instruments. It was the kind of motion that traveled through bone rather than sound, felt more than heard. Several scientists exchanged looks that bordered on fear. Satellite radar images arrived moments later, confirming ground deformation along Etna's eastern flank. The land was shifting downslope, not sliding yet, but creeping, as if gravity had gained patience and decided to take its time. Flank instability was one of Etna's most dangerous behaviors, precisely because it rarely announced itself with spectacle. Instead of a dramatic eruption, it threatened slow collapse, sudden fissures, and lava emerging far from expected locations. The first emergency meeting was convened quietly, without press or public notice. Models were loaded, assumptions tested, then discarded as outputs refused to stabilize. Etna's internal pressure distribution was changing faster than calculations could track. Another tremor rolled through the mountain, sharper this time. In nearby villages, people paused mid-conversation, glancing at hanging lamps that swayed just enough to raise questions. Dogs began barking long before humans understood why. Thermal cameras picked up faint heat anomalies, tracing a jagged line beneath the soil. It stretched downhill like a glowing vein, still hidden from view but growing longer by the minute. Magma was forcing its way sideways, exploiting fractures like water through cracked stone. One senior scientist muttered that this was the scenario everyone feared but rarely saw. Lateral magma intrusion meant the volcano's plumbing had rerouted itself, bypassing the summit entirely. If it broke the surface, it could do so anywhere along the flank. As dusk approached, steam vents appeared where none had existed before. White plumes rose quietly from fields and rocky slopes, carrying the sharp smell of sulfur. Farmers watched from a distance, unease settling into their chests. The fracture finally announced itself with sound. A deep, cracking report echoed across the mountainside, like thunder trapped underground. The ground split open along a line that had been invisible moments before, tearing soil and rock apart. Instruments went wild as pressure readings spiked, dipped, then surged again. The mountain seemed to hesitate, as though deciding how much force to release and where. There was no precedent for what the data suggested. Roads near the fracture buckled, asphalt splitting cleanly as the earth beneath it shifted. Stone walls that had stood for generations leaned and collapsed, victims of motion too slow to outrun and too powerful to resist. Authorities issued their first warnings, carefully worded to avoid panic. People were advised to stay alert, to prepare, to listen. No one used the word evacuate yet, but it hovered unspoken in every sentence. Gas levels rose sharply in low-lying areas, invisible and deadly. Carbon dioxide pooled silently, displacing oxygen and suffocating livestock before anyone realized what was happening. Farmers fled their fields, carrying children and shouting warnings that spread faster than official messages. Night fell, and with it came a new terror. The fracture began to glow faintly, a dull red line pulsing beneath thin layers of soil. Heat shimmered in the air, distorting the stars above it. A section of ground collapsed into the fracture with a roar that echoed for kilometers. Dust and steam exploded upward, briefly illuminated from below by incandescent rock. The mountain had opened its skin. Lava emerged not in a fountain, but as a slow, deliberate flow, oozing from the fracture far from any known crater. It moved like a living thing, advancing quietly, consuming grass, fences, and stone without urgency. This confirmed what scientists had feared. Etna was erupting sideways, releasing magma through its flank rather than its summit. The rules had changed, and with them, the margins of safety. Evacuation orders followed swiftly. Sirens wailed through the night, cutting through fear and disbelief. Roads filled with headlights as families fled, unsure of where the danger truly lay. The fracture continued to propagate, splitting into branches that glowed and hissed. Each branch represented another possible outlet, another unpredictable threat. Models failed entirely now, overwhelmed by complexity. Ash began to fall, light at first, dusting rooftops and cars like gray snow. It stung the eyes and coated lungs, turning breath into effort. The air tasted of metal and smoke. Seismic activity intensified, not as violent jolts, but as constant grinding motion. The mountain was rearranging itself internally, blocks of rock shifting against each other under forces beyond comprehension. A secondary collapse sent shockwaves through the flank, triggering landslides miles away. Entire hillsides slumped, carrying trees and soil downslope in slow, unstoppable motion. And communication networks strained under the weight of emergency traffic. Power flickered as ash interfered with lines and substations. Data feeds became intermittent, forcing scientists to work with partial information. Despite the chaos, Etna did not unleash a towering explosion. Instead, it bled energy through cracks and flows, expressing its violence through change rather than spectacle. By dawn, the landscape was unrecognizable. New lava fields steamed where vineyards had been. Roads ended abruptly at fissures that exhaled heat and gas. The fracture itself had widened, a gaping wound etched into the mountainside. It stretched farther than anyone had predicted, a reminder of how little humans truly understood the forces beneath them. Pressure readings finally began to decline, a slow easing that suggested the magma had found temporary release. No one celebrated. Relief was cautious, fragile, and incomplete. Scientists worked through exhaustion, documenting every detail. This event would rewrite textbooks, challenge assumptions, and force new questions about volcanic behavior worldwide. As the sun rose higher, helicopters surveyed the damage. From above, the fracture looked like a scar carved by something deliberate and ancient, cutting across terrain without regard for human boundaries. Villages stood empty, their streets silent beneath drifting ash. Doors remained open, abandoned in haste, evidence of lives interrupted by forces beyond control. The mountain itself seemed quieter now, its rumbling subdued. Steam rose gently from cooling lava, and birds cautiously returned to the sky. Yet no one trusted the calm. Etna had not finished speaking. It had merely paused, gathering itself after reshaping its own body. Geologists noted that the flank had permanently shifted, altering slopes and stress fields. This was not a temporary event, but a structural transformation. Centuries from now, layers of hardened lava would record this moment, a thin line in the geological record marking the night Etna chose a new path. The fear that lingered was not of fire alone, but of uncertainty. If Etna could fracture here, it could fracture elsewhere. The mountain had demonstrated its capacity for surprise. Emergency shelters filled with displaced families, their conversations hushed and fragmented. Children asked questions adults struggled to answer honestly. Scientists addressed the public with careful words, explaining what was known and admitting what was not. Transparency became a necessity, not a choice. As days passed, activity continued at a reduced pace. Lava advanced slowly, predictable now, but still unstoppable where it flowed. Engineers began planning barriers and channels, knowing such measures were temporary at best. Nature allowed mitigation, not control. The fracture cooled gradually, its glow fading to dull heat. Steam thinned, replaced by silence that felt heavy rather than peaceful. Etna stood changed, its silhouette subtly altered against the sky. The mountain had not grown or shrunk, but it had shifted, like a creature adjusting its stance. For those who studied it, the event became a lesson in humility. Data, models, and experience had all been challenged by reality. For those who lived near it, the lesson was more personal. The ground beneath their feet was alive, capable of movement and decision. As reconstruction plans began, debates erupted about where it was safe to rebuild. Lines were drawn, erased, and redrawn again. The fracture remained visible, a reminder etched into stone. Tourists would one day stand near it, marveling at its scale, unaware of the fear it once inspired. Etna continued to emit heat and gas, reminders that the system was still active. Dormant did not mean asleep, only waiting. The mountain had not destroyed Sicily that night. Instead, it had reminded everyone of its power, choosing restraint over annihilation. In the quiet aftermath, scientists agreed on one truth. This was not the end of Etna's story, but a chapter that would echo far beyond its slopes. The earth beneath humanity was not fixed or stable. It moved, adapted, and broke when pressures demanded it. Etna's flank fracture would become a case study, a warning, and a symbol of nature's unpredictability. And long after the lava cooled and the ash washed away, the memory of that night would remain, as enduring as the scar carved into the mountain's side. The mountain did not settle quietly. Even after the initial fracture stabilized, subtle tremors rippled through the flank. These were no longer large quakes, but persistent pulses that reminded everyone the mountain had not relinquished control. Each tremor bent trees slightly, rattled loose stones, and whispered the possibility of further movement. Scientists deployed additional sensors along the newly fractured zones. Ground-penetrating radar detected molten pockets pressing against brittle rock, each one a potential source of secondary fractures. The mountain's internal plumbing was now irregular, unpredictable, and capable of sudden improvisation. Villages cautiously repopulated, but the anxiety remained palpable. Farmers measured the soil carefully, noticing subtle shifts that could compromise irrigation or foundations. Crops had begun to wilt in areas where gas had seeped unnoticed. Livelihoods hung in delicate balance. Hydrologists were called to analyze the impact of the fracture on underground aquifers. Water tables had shifted slightly, changing the flow of springs and wells. Some areas began showing signs of contamination from minerals released by fractured rock. The disaster was not over. It had only transformed into a slow-moving hazard. Tourists cautiously returned to vantage points, taking photographs of the scarred mountain. For many, the aesthetic drama was compelling. Yet for scientists, every photo was a piece of data. Heat signatures, vegetation damage, and slope angles were logged meticulously. Nature had become both spectacle and laboratory. A week after the initial fracture, a small secondary collapse occurred near one of the branches. Stones slid down a slope silently at first, then with increasing speed, leaving gouges in the landscape. Though no one was hurt, the incident reminded observers that Etna's flank was far from stable. Drone operators reported new fissures emitting faint smoke. Thermal imaging showed magma creeping under the surface, exploring new paths. The fracture was evolving, not healing, like a living wound. Scientists updated hazard maps daily, but every forecast came with a growing caveat: uncertainty. Seismologists noticed a shift in frequency. Low-frequency rumbling dominated, suggesting deep rock movement rather than surface shaking. This was a signal that stress was redistributing internally. The mountain had become a complex system, reacting to its own reshaped geometry. Emergency response teams conducted drills, simulating evacuations along the eastern slopes. Roads had been compromised, and some villages relied on precarious detours. The fracture had not just shifted the earth, it had rewritten the logistics of survival. Geologists collected samples of newly exposed rock, noting temperature anomalies and unexpected mineralization. The fracture had uncovered materials that had not been seen for thousands of years, preserved under intense pressure until now. Etna's interior was revealing secrets as it healed. Media coverage intensified, but scientists struggled to communicate the nuance. Headlines warned of a sleeping giant, or Etna's new fury, yet reality was more complex. A mountain rearranging itself, slowly, deliberately, without catastrophic eruption, yet with risks that demanded respect. Volcanologists debated long into the night, analyzing why the fracture occurred where it did. Some suggested it was residual stress from prior eruptions. Others proposed that underground magma channels had migrated laterally over decades, weakening the flank gradually until failure. Consensus remained elusive. Meanwhile, minor tremors continued, and small fumaroles appeared in unexpected locations. Each fumarole carried subtle chemical signals that hinted at the composition of molten rock below. Monitoring teams analyzed sulfur dioxide, carbon dioxide, and other gases continuously, looking for patterns. Residents adapted to a new rhythm of life. Schools taught children to recognize early signs of tremors. Communities created evacuation routes, not out of panic, but practicality. Daily life and the shadow of the fracture intertwined, a constant reminder of nature's authority. Satellite imagery revealed that the fracture had altered drainage patterns on the slopes. Rainwater pooled in new depressions, eroding channels and forming unstable banks. Engineers warned that heavy rain could trigger landslides, compounding the hazard already present. Scientific teams debated whether controlled explosions or other interventions could stabilize parts of the flank. Many argued against it. Interfering with a mountain of this scale risked unpredictable consequences. Nature, it seemed, had the final word. The fracture's glow faded slowly over weeks, but never vanished entirely. At night, thermal imaging showed residual heat moving like slow currents under the earth. The mountain's circulation was ongoing, a reminder that Etna had entered a new phase of activity. Researchers published preliminary findings. The event was unprecedented in recorded history, a lateral fracture of such scale without a major eruption. Papers described the structural changes, magma redistribution, gas emissions, and surface deformation in detail. Etna had rewritten the textbook. Volcanic hazard agencies updated building codes for the region. New constructions were advised to avoid vulnerable slopes, and existing structures were assessed for stability. Even decades-old walls were scrutinized for damage from subtle ground movement. Psychologists studied the local population, noting persistent anxiety even after the immediate danger passed. Living near an unpredictable volcano reshapes perception of risk, health, and community cohesion. People learned to respect the mountain, balancing fear and fascination. Geotechnical engineers mapped landslide potential using updated topographical data. The fracture had created weak zones along the flank where even minor triggers could provoke rock movement. Early warning systems were enhanced, integrating seismic, thermal, and gas data. Across Europe, Etna's behavior prompted a review of other volcanoes with steep flanks. Scientists questioned whether similar hidden weaknesses existed elsewhere, unseen until a crisis emerged. The Etna fracture became a reference point for understanding lateral eruptions globally. A month after the fracture, small tremors persisted, but the slope appeared stable. Thermal cameras detected slow cooling, yet subsurface currents of magma continued to shift. Etna was no longer simply a stratovolcano, it was a dynamic system of interacting pressures and flows. Local governments conducted drills with broader populations, integrating the new understanding of hazard zones. Communication protocols were revised to include real-time updates on flank stability, not just eruptive activity. Researchers discovered minor seismic swarms in areas adjacent to the fracture. These were not immediately dangerous, but indicated that stress had been redistributed across the mountain. Etna's internal equilibrium was delicate and ongoing. Environmental scientists measured the impact on local flora and fauna. Heat, gas, and ash affected vegetation, altering soil composition and plant growth patterns. Wildlife migrated temporarily, adapting to the changes in terrain and microclimate. Historical comparison revealed that previous flank collapses were always linked to eventual eruptions, but Etna had deviated. Understanding why could provide critical insights into future risk assessment and volcanic behavior modeling. Tourist observation points were modified for safety. Visitors could witness the scarred mountains safely, while monitoring stations continued to gather data uninterrupted. Tourism became a careful balance between curiosity and caution. Volcanologists hypothesized that the fracture might stabilize permanently, creating a new slope profile and venting pathways for future magma flow. The mountain had changed its anatomy, and scientists could only predict, not dictate, the consequences. Infrastructure teams worked on reinforcing roads and bridges near the fracture. Ground movement had compromised foundations, requiring adaptive engineering to maintain access to remote villages. Evacuation routes were improved with early warning sensors embedded in the ground. If future shifts occurred, alerts could be sent instantly to residents, reducing the risk of human casualties. Media coverage became more scientific, emphasizing data, maps, and risk management. Sensational headlines were replaced by nuanced reporting, acknowledging both the danger and the mountain's complexity. International agencies offered assistance and expertise, collaborating with local scientists to monitor Etna. Global volcanic networks used the event to refine models for other active stratovolcanoes. Long-term monitoring plans were implemented. Multi-year studies would examine magma migration, flank stability, gas emissions, and the impact of fractures on surrounding ecosystems. As the landscape slowly healed, lava cooled into new formations. The scar on Etna's side became a permanent geological feature, visible from miles away and marked on maps for the first time. Villagers returned cautiously, rebuilding homes, schools, and businesses with new awareness of risk. Community resilience became a central theme in local planning. Scientists reflected on the event as a turning point in volcanology. Etna had defied conventional understanding, demonstrating that large-scale lateral fracturing could occur without immediate explosive eruption. The mountain's behavior continued to challenge assumptions. Each tremor, gas reading, and thermal anomaly reminded observers that Etna remained dynamic and alive. Environmental studies documented changes in river flow, sedimentation patterns, and soil chemistry. The fracture had consequences far beyond immediate destruction, shaping ecosystems for decades to come. Education programs incorporated the event, teaching students about geology, risk management, and community preparedness. Etna became a living classroom for the study of complex natural systems. Geophysical models were updated to include lateral intrusion, flank failure probability, and unpredictable magma pathways. These models informed both scientific understanding and practical hazard planning. Communities developed local emergency networks, ensuring rapid communication and coordination in the event of future activity. Lessons learned from the fracture improved regional resilience. Seismographs and thermal sensors remained in place indefinitely, providing continuous data to scientists. Real-time monitoring had proven critical in predicting the mountain's behavior. The fracture scar became a site for interdisciplinary study, attracting geologists, ecologists, engineers, and urban planners. Collaboration between fields became essential to understanding the mountain's evolving dynamics. Media and educational outreach emphasized both the danger and the wonder of volcanic processes. Public engagement helped communities accept ongoing monitoring and adapt to new risk realities. 2 months after the fracture, minor landslides occurred in peripheral areas, proving that the mountain system was still redistributing stress. Authorities responded quickly, minimizing impact. Researchers discovered previously unknown subsurface channels exposed by the fracture, offering new insights into Etna's magma transport system and thermal evolution. The event became a reference for hazard assessment worldwide, influencing planning, construction codes, and emergency response protocols in volcanic regions. Local and international scientists continued collaborative research, publishing findings that reshaped understanding of stratovolcano mechanics. The fracture's presence transformed tourism, education, and local culture. It served as a reminder of the mountain's power, beauty, and unpredictability. Over time, vegetation slowly reclaimed areas affected by heat and ash. New soil layers formed over cooled lava, creating a living laboratory for studying ecological succession. Communities adapted with resilience, integrating the lessons learned into daily life and infrastructure planning. Etna's flank fracture remained a focal point for research, observation, and cultural reflection. It had altered not just the mountain, but the human relationship with it. The mountain continued to exhale steam and gas quietly, a reminder of ongoing subterranean activity. Life on its slopes had changed, shaped by respect, vigilance, and adaptation. Even years later, the fracture scar would remain visible, a permanent testimony to the night when Etna reshaped itself and reminded humanity of the delicate balance between Earth and life.